Marilena Loverde today. Well, actually right now she's at the University of Chicago. So she got her PhD at Columbia. I won't say the year, but it wasn't too long ago. And then you went from there to Princeton? IAS, okay. There's nothing. So she went there to IAS for a postdoc, worked with Matthias Aldergaga in cosmology group there. Since then, she's gone to get a postdoc at the University of Chicago, KICP, Copley Institute for Cosmological Physics. She works there with Wing Hu and various other people. She, I guess last year in the job cycle, she accepted a position, faculty position, assistant professor at Stony Brook, where she will be joining a burgeoning cosmology effort there. So they just hired 3 or 4 cosmologists, so she will be a theorist working at the Yang Institute.
Yep.
With in there. So it's a pleasure to have her here today. She has broad range of expertise in various cosmological areas. So today she's going to be talking about neutrinos and large-scale structure, so that should be interesting. So go ahead.
Thanks a lot. It's nice to be here at Texas in Texas. It's a really nice institute going on here also. So today I'm going to talk about cosmic neutrinos and large-scale structure. And I know there's a range of backgrounds in the audience, so I'm going to move back and forth a little bit in terms of trying to be elementary about some of the astronomy things and elementary about some of the particle physics things, but please stop and interrupt me if you have any questions. Just to set the stage, this is a slice of a simulation of the large-scale structure of our universe. So this is a cold dark matter simulation, and what you see here is this big filament, this network of filaments and voids, and at the nodes between these filaments here are these little blobs, which are dark matter halos, which is where clusters of galaxies and galaxies themselves reside. So when I picture the large-scale structure of the universe, this is often what I'm picturing here, where even though this simulation is only cold dark matter, and we know that there's baryonic matter, which makes up things like galaxies and us, the cold dark matter tells most of the story of what's going on with the large-scale structure. So the baryonic matter follows very closely this cold dark matter, and on these very large scales, I think this is a, should I forget, 100 megaparsec box or something. These, the cold dark matter and baryonic matter look very similar. So this is a slice from a simulation by these authors, but now what I want you to have in mind is that this is not the whole story when it comes to thinking about the large-scale structure of the universe. Our universe has at least 2 types of dark matter in it. Cold dark matter, which is responsible for seeding the structure, which grows gravitationally and makes all the stuff that we see around us. But our universe also has dark matter in the form of massive neutrinos. And we don't know the masses of the neutrinos, and the masses will determine, how large the masses of the different neutrinos are will determine their clustering properties more precisely. But we know that at least some of the neutrinos have mass, which I'll discuss more shortly. And therefore, they'll participate in clustering as well. So this is a slice of a simulation showing what the neutrinos would be doing in a universe with this cold dark matter background. So the picture that I want you to have in your mind is that the large-scale structure of our universe is already very rich with just the cold dark matter and the baryons, but is much richer. And hopefully in the next sort of 5 to 10 years, this neutrino dark matter is going to become a part of the description of the large-scale structure of our universe. So that's where I'm going, and the reason that we haven't had to take into account the neutrino dark matter so far is that it's a tiny fraction of matter density. So there's actually a lower bound on the energy density in neutrinos relative to the energy density in other forms of matter, cold dark matter, baryons, and neutrinos, and that's a lower bound of about 0.5%. So the energy density in neutrinos today is tiny, and we've so far not had to take this into account in order to describe current observations. But in the not too distant future, we'll actually have observations that are precise enough that we'll need to explain the neutrinos. On the other hand, even though this is a tiny amount of energy density, there's a huge number of neutrinos. So neutrinos are almost as abundant in the universe as cosmic microwave background photons. There's about 10 to the 10 neutrinos for every baryon, similar to this number of the number of cosmic microwave background photons compared to the number of baryons. So they're very abundant in the universe. So where I'm going to get to later is some discussion of what the effects of neutrino dark matter are on the large-scale structure of the universe. And one thing that it affects is the total abundance of cold dark matter halos that host clusters of galaxies and clusters. The neutrino dark matter has effects on the spatial clustering of dark matter halos. That is, what are the statistics of how, given that you have a galaxy or a galaxy cluster or a halo here, what's the excess probability above random of having some halo a distance away? And finally, because neutrinos have mass, they actually end up accreting onto these cold dark matter halos, participating in gravitational clustering, and creating sort of puffy neutrino halos around all the dark matter. So I'm probably going to just focus on this second topic today, but that's the trajectory of where I'm going after. Oh, that's just drawing halos.
Oh,
So,
okay.
yeah, just to
To
clarify. No, it doesn't mean anything. I drew little circles around where there would be galaxies. So,
How precise is this 10 to the 10th relationship?
so actually, I'll get there. Not exactly that, but ask me again once I discuss how we know how many neutrinos there are. Okay, so that's where I'm that's the stage, and then where I want to go with my talk, and then here's the outline in more details. First, I'll review some basic properties of neutrinos, then discussing cosmic background neutrinos, where the cosmic neutrino background comes from, the general physical effects of neutrinos in large-scale structure, and then some of these particular effects that I've been thinking about in the observational prospects. So first off, neutrinos. What do we know? Well, we know that there are 3 neutrino flavors, one for each of these light-charged leptons, electron, tau, and muon particle. And for each of these flavor eigenstates, there's a mass eigenstate. So we have 3 flavor eigenstates and 3 mass eigenstates. But the neutrino oscillation data tells us that the flavor eigenstates and the mass eigenstates don't coincide. There's some unitary transformation that relates the two. And because of that, that can only happen in a case where there is some mass associated with these So 3 flavor eigenstates, 3 mass eigenstates, and these from the oscillation data, which tells us that the flavor eigenstates and the mass eigenstates aren't the same, we learn something about the splitting between these different mass eigenstates. So the solar neutrino oscillation data gives the difference of the squares of 2 of the mass eigenstates to be about 10 to the minus 4 eV squared. And atmospheric oscillation data gives the difference between 2 of the other mass eigenstates to be about 10 to the minus 3 eV squared. So this is what we know about the neutrino masses, but we don't know we only know these quantities which tell us the differences between the mass squares. We don't know what the absolute scale is of the neutrino mass roughly, or what the individual masses, nu1, nu2, and nu3 are. But there are sort of 3 qualitatively different ways of arranging the neutrino masses that are consistent with these 2 splittings, which we have here. One is the normal hierarchy, where I set one of the masses to be about 0, and the next most massive state has a mass of about 0.01 eV, and the most massive state has a mass of about 0.05 eV. There's an inverted hierarchy, where one of the masses is close to 0, and the other 2 are about 0.05 eV. And then, if any one of the neutrino masses is about 0.1 eV or large compared to these splittings, then all 3 of the neutrino masses are roughly the same. So there's still some tiny splitting here, but it's sort of irrelevant for asking what the mass scale of the neutrinos is. So the punchline that I want you to remember for this is that of these different ways of writing down neutrino masses that are consistent with the oscillation data, there's a lower limit on what the mass of one of the most massive eigenstates is. That is, there's at least one neutrino with a mass greater than 0.05 eV, or the sum of the neutrino masses is at least 0.06 eV. That's the smallest number that I can get that's consistent with the neutrino oscillation data. But we don't know the absolute scale at all. So here's a cartoon outlining some of the things that we know about neutrino mass. So here I've written down at least one mass is bigger than 0.05, so that's a lower bound we get from oscillation data. And then there are, of course, upper bounds from various other types of experiments. On the particle physics side, the most stringent bound on the neutrino mass comes from experiments which are looking for the endpoint of tritium beta decay. And this sets an upper limit on the effective mass of the electron neutrino to be less than 2 eV. And in the not too distant future, there are other experiments like Ketrin and Project 8, and eventually even Ptolemy perhaps, which will bring this upper bound on the effective mass of the electron neutrino from 2 eV down to about 0.2 eV. But even this is it's challenging. These experiments will do better than this in the very distant future, but it's challenging to get below masses about tenths of an eV with tritium beta decay. On the other hand, the constraints from cosmology are what are currently set the best upper limit on the neutrino masses. So these numbers here are from Planck data in combination with other data sets or just Planck data alone. And these constraints give 95% upper limits on the sum of the neutrino masses between a half an eV all the way down to about 0.2 eV, depending on which data sets that you combine. So this limit, just to remind you, this is the sum of all three masses. So this is already an order of magnitude better than this, which is just the limit on one of the mass eigenstates, which would give, if there was a detection here, then the sum of the masses would be something like 6 eV. So cosmology is currently providing the most stringent upper limits on the total masses. And as future cosmological data sets get stronger and stronger, these upper limits will come down and lead to, hopefully, a future detection of the absolute scale of the neutrino mass from astrophysics. So that's exciting because we have a strict lower bound and then these upper bounds coming down. And what I want to emphasize is that this is exciting because from a cosmology perspective, we anticipate needing to include neutrino mass to explain data sets. If you didn't see this or you see something else that's inconsistent, that would be also very exciting because within the standard cosmological model, we have firm predictions for the abundance of neutrinos and so on. It's interesting theoretically and observationally. There's lots of different types of experiments from cosmic microwave background experiments, which mostly get information about neutrinos from lensing to large-scale galaxy surveys that will get information about massive neutrinos from a variety of effects. The types of numbers that people are quoting from combining these future data sets are limits, sort of 1 sigma errors on the sum of the neutrino mass of about 0.02 eV, which is sufficient to detect that minimal scenario of 0.06 eV at 3 sigma level. So that's neutrino mass, but there's of course all kinds of other questions about neutrinos that we don't know the answer to. We don't know, never mind the value of the mass, we don't know where the neutrino masses come from. We don't know whether there are additional sterile neutrinos that don't interact via the weak interaction. We don't know whether perhaps neutrinos are helpful in transferring some lepton asymmetry. They're generating some lepton asymmetry, which gets transferred into a baryon asymmetry and allows there to be a matter-antimatter asymmetry in our universe. So there's all kinds of interesting things to think about with neutrinos. And cosmology, many of these questions can have physical signatures in cosmology, but the two things that I'll talk about most today are how cosmology can inform the mass scale of neutrinos, and a little bit about whether there are additional sterile neutrinos. Okay, so it's an overview of neutrinos. Now let's talk about how neutrinos fit into the thermal history of the universe. So this is a timeline showing a thermal history of the universe where time is increasing this way and the universe is getting colder and things are getting more rarefied, whereas previously things were hotter and denser. And I've added to this timeline a couple of important epochs. So we're very familiar with the recombination of hydrogen, and shortly prior to that, the decoupling of cosmic microwave background photons from the photon baryon plasma, which happened when the temperature of the universe was about 0.2 eV. Prior to that, there was Big Bang nucleosynthesis. And at much earlier times, when the temperature of the universe was about an MeV, back here, neutrinos were actually in thermal equilibrium with everything else. So at temperatures above about an MeV, neutrinos were in equilibrium with the other stuff that was around at that time. Just prior to that temperature, the other things that were around were photons and electrons and positrons, protons and neutrons, of course, as well. But since these things were in thermal equilibrium, they all had a common temperature, and in particular, the temperature of the neutrinos is the same as the temperature of the photons, which is just dropping off as the universe expanded. After about an MeV, neutrinos stopped scattering frequently with the electrons and positrons and decoupled. And the temperature of the neutrinos from that time until today should have remained largely unchanged, other than the fact that the temperature drops as the universe expands. The temperature of the cosmic neutrino background should be dropping with 1 over the scale factor. So prior to neutrino decoupling, there was a common temperature with the photons. And after neutrino decoupling, the neutrino temperature just kept on redshifting up until today. Now we measure and since the neutrinos were in thermal equilibrium and decoupled while they were relativistic, this one number, the temperature, completely specifies their distribution function. So the number density of neutrinos is just given by the temperature cubed, integrating over the Fermi-Dirac distribution, and their energy density at early times when they're relativistic is just given by the temperature to the 4th power. So this is starting to come back to your question a little bit. So these predictions are firm in the sense that they rely on neutrinos being in thermal equilibrium at early times. So all I need to do is specify the temperature in order to understand their number density and energy density and temperature today. So requires thermal equilibrium at early times. This is not crazy high energies, and that they have not interacted much between then and today, at least other than gravitationally. Now, what is this number, the neutrino temperature? Well, that's actually something we can calculate. We measure the temperature of the cosmic microwave background photons quite precisely. And we know that photons and neutrinos had a common temperature before neutrinos decoupled. It turns out that photons, CMB photons, are a little bit hotter than neutrinos today because they received a little bit of energy injection when electrons and positrons annihilated. So after the neutrinos decoupled, when neutrinos decoupled, electrons and positrons were still in thermal equilibrium. Shortly thereafter, electrons and positrons annihilated, and that extra energy got injected into the CMB and thermalized. But that extra energy that gets injected into the CMB is something that we can calculate. And that gives you a relationship between the CMB temperature and the neutrino temperature, which comes from at least this approximately equal to 11/4 to the 1/3 comes from just the counting of the number of particles before and after this epoch. And we know the temperature of the photons, so that gives us the temperature of the neutrinos, which is 2 Kelvin. And from this temperature, we can calculate what the number density is, and that's about 336 per centimeter cubed. So I would say that this number is theoretically on pretty solid footing in the sense that within a standard cosmology, and these are at energies which aren't incredibly high and epochs where we think we understand the physics pretty well, one backs out this number with only the calculation of the temperature. Of course, this has actually been measured to some extent, which I'll show you in a minute. But does that answer your question?
Almost.
Okay.
Where is the depth of the depth?
Oh, this is the number of neutrinos that you predict to exist, and then we know the number density of baryons. And so this is about 10 to the, the number density of baryons is about 0.1 per cubic meter in the universe. So the 10 to the 10 comes from, 10 to the 6, 7, 8, 9. Okay. A little bit about how we know about where these constraints come from is as follows. The radiation density in the universe at early times when neutrinos were relativistic, before the time of the cosmic microwave background forming, the radiation energy density is composed of 2 pieces, which is the one component coming from the cosmic microwave background photons, and another part coming from the cosmic neutrino background. And this is written in this clever way where the number of neutrinos here is written as n effective. I've factored it out. So the total radiation energy density is CMB part plus a neutrino part, and there's some various factors in here like 2 and 7/8, which have to come from neutrinos and antineutrinos, and then the fact that these are fermions gives this factor of 7/8 with respect to the photons, which are bosons. And then there's this number n effective, which in the standard model of particle physics is 3. We have 3 species of three different types of neutrinos. But because we have constraints on the energy density and radiation in the universe, from measurements of the cosmic microwave background, and we know the photon energy density pretty well, we can turn constraints on the energy density and radiation into constraints on the number of neutrino-like degrees of freedom, where neutrino-like means something with this temperature that we expect, and something that's a fermion, and so on. And a really cool thing is that when you look at cosmic microwave background data, like that from the Planck satellite, and you ask how many neutrino-like degrees of freedom there were early on, you get a number which is about 3, which is totally consistent with what we expect from the standard model of particle physics. So this number can be interpreted as a constraint, as a measurement of the cosmic neutrino background, but at early times when neutrinos were acting like radiation. And these error bars are sort of numbers like 3 plus or minus about 0.2. Those constraints will only improve with this next generation of CMB experiments like Advanced ACT and ST-T3G and so on. So I think this is really cool. It's a nice confirmation. It's 2 different types of physics are sort of coming together and giving numbers which are very consistent. So a quick summary so far. There is a cosmic neutrino background. It has a density of about 300 particles per cubic centimeter and a temperature which is 2 Kelvin or 10 to the minus 4 eV. And this cosmic neutrino background has been detected in the cosmic microwave background in the form of extra contributions to the radiation energy density. On the other hand, the neutrino oscillation data says at least one of the neutrinos has a mass that's 0.05 eV. And so putting this mass together with this temperature of 10 to the minus 4 eV tells you that today, the typical velocity of these neutrinos is 1,000 kilometers per second or less if the mass is larger. So this comes back to massive neutrinos acting like a warm or hot dark matter component today. And the energy density in these guys, if their energy is dominated by their rest mass, then the energy density in massive neutrinos is just the sum of the rest masses times the number densities for each of the particles. So any measurement of this warm, hot neutrino dark matter component at late times is going to be a measurement of the neutrino mass since the number density is known. But again, within the standard cosmology, this is a firm prediction, and seeing anything different would be also very interesting and exciting. So the place to look for something which is warm, hot, dark matter is in large-scale structure. So these are slices from a simulation, a movie of a simulation by Andrei Kravtsov, showing the evolution of small density perturbations growing through cosmic time into the large-scale structure of the universe. And the claim is that massive neutrinos are going to alter this process in some tiny but hopefully detectable way. Yeah.
There's other questions.
Great.
I missed why the T nu and T gamma are not the same. Where did the 11th force to the 1/3 come from?
It comes from the fact that the gamma, the photons, get an extra kick of energy from when electrons and positrons annihilate. So neutrinos are no longer frequently interacting with the photons. So neutrinos cease to interact with the photons, but positrons and electrons are still in equilibrium when neutrinos stop interacting. So when those positrons and electrons annihilate and freeze out, that adds energy back into the photons and electrons and everything else. Yeah. Okay. Any more questions? All right. So how do you know the difference between things like neutrinos and things like baryons and cold dark matter by looking at large-scale structure? Well, the way that they behave differently is that their gravitational clustering properties are different. Particles which are cold and slow-moving, like dark matter and baryons, can clump easily, whereas quickly moving particles like neutrinos or some other exotic-like particles have large kinetic energies and do not gravitationally cluster so easily. For this cartoon, I'm thinking of baryons and cold dark matter as having approximately 0 velocity, which is just fine for the scales that I'm thinking about, whereas the typical velocity of neutrinos would be the temperature divided by the mass. Here's a cartoon illustrating more precisely what the effect what the different gravitational clustering of cold dark matter and baryons versus massive neutrinos, how that looks. So imagine I have this small scale density perturbation, which is composed of these cold dark matter particles, which are supposed to be blue, and the neutrinos, which are yellow. If this blob of stuff, the neutrinos and the cold dark matter, are initially coherent, if I start with this blob of stuff that's initially coherent, it will not stay that way for long. So the neutrinos, with their large velocities, can stream out of this overdense region, leaving behind the cold dark matter and baryons, which don't stream out. And so the cold dark matter and baryons will collapse a bit over their own self-gravity, but the only thing that's gravitationally clustering here is the cold dark matter and baryons. The neutrinos, if they have large velocities, can just stream out of this region, leaving that other stuff behind. Now, if I had a much larger scale density perturbation, the neutrinos will still move, but if the typical distance the neutrinos travel is small compared to the size, the physical extent of the density perturbation that I'm considering, then this free streaming of the neutrinos is not very relevant on this very large scale. So for a very large perturbation, the cold dark matter and baryons and neutrinos will all grow together. So the consequence of this is that small scale density perturbations and large scale density perturbations grow differently in this cosmology. The small scale ones don't hold on to their neutrinos, and that means that there's not neutrino perturbations on small scales, and it also means that the cold dark matter and baryons grow more slowly because there's less stuff contributing to this gravitational potential. Whereas on these large scales, the perturbations are composed of cold dark matter, baryons, and neutrinos all growing together, and if you were only looking at these very large scales, you wouldn't be able to distinguish between cold dark matter and neutrinos. They're all behaving in the same way. So the growth of density perturbations is scale dependent. And the physical scale that separates these two regimes is the typical distance a neutrino can travel in a Hubble time, which depends on the velocity, which depends on the temperature, which we think we know, and the mass, which we think we don't know. The physical effect of this on observations of the large-scale structure is to suppress the typical amplitude of density perturbations on small scales. So this is this plot shows the change in the power spectrum, which you can think of as the typical amplitude of density perturbations on a given at a given scale, where these are small scales on this side with large Fourier wave numbers, and large scales on this side with small Fourier numbers. So the more mass, the more of the total matter density in the universe that you put into massive neutrinos, the greater the suppression is in the density perturbations. And the location of this suppression depends on the mass of the particles as well, although it's a bit hard to see. On this scale, these different masses are only different by factors of 2. And this is the log scale, so it's not super clear. But this is one of the main physical effects of massive neutrinos on large-scale structure. And it's sort of the primary way that constraints on the total mass density of neutrinos, constraints on the masses of the neutrinos are derived from data sets like the CNV. So the physical effect of these massive neutrinos is to suppress the amount of structure on small scales, and that suppression in structure decreases the amplitude of these density perturbations, lessens the amount of gravitational lensing that the cosmic microwave background experiences, and so on. And that allows one, by asking how much suppression can be tolerated within the given data sets, you can get constraints on the total mass of neutrinos. So this is a plot from the Planck 2015 papers showing probability contours limiting the probability contours on the total mass in neutrinos from different combinations of Planck data sets. So depending on what parts of the Planck data sets you look at, temperature and polarization, for instance, or including their lensing reconstruction, you get slightly different constraints on the amount of neutrino mass, but there's a very firm limit of something like less than 1/2 an eV, if not much stronger than that by combining these different data sets.
The question.
Yes.
So the proton on the left,
Yes.
and inverted case is slightly larger suppression is red.
Yes.
Because the two mass eigenstate heavier than other one.
Yeah, so for this case, so for me, normal math hierarchy here means one neutrino, which is 0.05, and one, which is 0.01.
Right.
Whereas inverted means two, which are 0.05. So the greater suppression comes from the larger sum of the masses.
In that case, you assume the all three eigenstate the same flux and
Is the same, I'm sorry?
same density.
Yeah, that's right. So they all have the number density for each eigenstate, I'm assuming is the sort of standard number of 112 per centimeter cubed. But I'm just adjusting the mass density. What sets this suppression here is just the mass density, which is the sum of these two quantities. There is a little bit of sensitivity to the mass in terms of where the suppression occurs, and heavier, it's not precise. People often say that these constraints just depend on the total amount of neutrino mass, but that's actually not precisely true. There's a little bit of a logarithmic sensitivity. There's a little bit of a difference between having 1.3 EV neutrino and 3.1 EV massive neutrinos, because the 0.3 EV guy becomes non-relativistic earlier than the 0.1 EV, but people are a bit sloppy about that.
Just a quick question.
Yes.
One of the problems I have with the CMB is that lots of parameters are being pulled out, and they're not all independent with each other. So the number of neutrinos has a lot of covariance with the value of the Hubble constant. So is there any other parameter that this is heavily covariant with in the analysis? Because this is not an eigenvector when you pull out all of these parameters. They really are related with each other.
Yeah.
What is this sensitive to, mostly?
Yeah, I think, yeah, that's a good question. So, let's see, it depends a bit on which data set you're looking at.
Well, I don't want to stop you. Maybe it's not an easy question to ask, and I'll ask it.
Yeah, I guess,
Another time.
so there are some types of physical, so for instance, in the main constraint from the CM, I mean, a lot of this interesting information that's coming from the CMB, actually, yeah, okay. Let's see if this is visible on this plot. So the effect of massive neutrinos sort of decreases the clustering matter, but that's degenerate with just how much perturbation, what the amplitude of perturbations is to begin with, in principle. Although it's not precisely true, because if I started with a power spectrum that just looked like this, the cosmology would be a bit different, because with neutrinos, these scales are growing differently than these scales. So I'm afraid I'm actually going to end up getting a bit more confusing. I was intending to.
Well, that's fine.
But,
Don't need to waste any more time on my question.
Yeah, no, it's
not
fine.
that important.
Yeah. I think if you were, I guess what I want to say is, I think if you were just looking at the CMB, this would be trickier. But if you have CMB information plus information from Galaxy surveys, the more different sources of information you have at different times, the harder it is to play games with.
Except then you have astrophysics, and astrophysics is nowhere near as clean as this in
Yeah,
terms of the
that's
physics,
right.
especially when you're talking about small-scale structure, which is not a linear perturbation.
Yeah,
It's a nonlinear perturbation.
That's right.
So,
Yeah. And I agree.
stay away from astrophysics. It's safer.
No, that's exactly where I'm going though.
Okay.
So I'm going to go to the nonlinear regime.
So there's S and the AO, that's just the cause pressure H. That's breaking into NRC, which is where you're getting better constraints.
Yes, that's right. And then one of the interesting things I was going to say is that I think there's something interesting going on where you add the Lowell polarization, and that adds information about tau, the optical depth, which sets the overall scale of the power spectrum, and the overall scale of the power spectrum is degenerate with the neutrinos a bit. Yeah. Yes.
So if you keep the sum of the masses the same and increase the number of neutrinos, does that make a difference to analysis?
Yeah, in principle, that comes back to, if all you were measuring was this energy density here, that wouldn't be true, but in there's actually a bit more information, because if you decrease the number density but increase the masses, then they would become non-relativistic sooner and act more like
I'm not
cold
saying
dark
the
matter.
number, but say if I don't have to play with 3 species, or have 4 or 5 species of neutrinos.
Yeah.
But I'm not assuming certain mass relation. Let's say to be more generically, could be degenerating mass. So is your analysis sensitive to more to the sum of the masses, or more to say actually distinguish how many species of neutrinos?
So these measurements of the number of effective degrees of freedom are, I mean, anything that's relativistic at early times is going to contribute here.
Yes.
So that gets tricky to add. That's where it gets tricky to have sterile neutrinos that are populated at that level, unless they have their fractional abundance is way less than the regular neutrinos. Yeah. Sorry, I guess, what is the precise question? Sorry.
So my question is, if we don't change the sum of the masses, we
Yes.
still keep the sum of the square mass the same, but we say instead of distribute that into 3 flavors, we distribute that into 4 flavors.
Yeah.
And does that make a difference to our analysis?
Yeah, I think it would make a small difference to these curves right here, but very small. So these curves are like, to lowest order, they're just sensitive to this combination, but there is some logarithmic sensitivity to the actual masses. Okay, and then again, data sets like these, for instance, future CMB lensing measurements may, are forecasted to be able to arrive at a 3 sigma detection of even this normal hierarchy. So that's cool. All right. Now, what I want to emphasize is that massive neutrinos don't just change the amplitude of the perturbations, but they change the growth rate of the perturbations. And this is key, and this is one of the things that helps just break some of these degeneracies in the data sets, is that not just the amplitude, but also how fast those perturbations are growing is affected by massive neutrinos. And I discussed how this suppresses the matter power spectrum, which is tested via lensing and galaxy power spectra. It also suppresses the number of massive objects. It makes it more unusual to have very large density perturbations that can form things like galaxy clusters. And that's interesting, and massive neutrinos have been used to interpret some of the tensions in the flight data. Massive neutrinos, of course, eventually accumulate around the cold dark matter halos. Finally, the thing that I'm actually just going to spend the next 15 minutes talking about is how this changed growth rate of density perturbations causes this quantity called a halo bias to have a scale dependence. And this is an interesting new signature of massive neutrinos in large-scale structure, or possibly a systematic that I've been thinking about. So now I want to discuss this particular physical effect of the cosmic neutrino background on halo clustering, which is a scale dependence of the halo bias. So just a quick discussion of what halo bias is. This is a slice from the Millennium simulation showing the distribution of matter on very large scales. And this is a slice showing the distribution of galaxies on very large scales. And what you can see is that if I'm looking at these very zoomed out slices of the universe, that the galaxy distribution and the matter distribution are very, very similar. And if I restrict my analysis to looking at very large scale fluctuations in the density and fluctuations in the density of galaxies, these two quantities are actually just linearly proportional. The fluctuation in the number density of galaxies from place to place is just proportional to the fluctuation in the mass density from place to place. And this proportionality constant is called the bias. Here, galaxies live in halos, so I'm going to use this term halo bias and galaxy bias to be synonymous, even though that's not precisely true. On these very large scales, it's an acceptable use of language. So let's think about, so where I want to go with this is that this is a classic picture of very large scale galaxy bias. And here I just have fluctuations in the mass density. But now in our universe we have two types of dark matter. We have the cold dark matter and the neutrino dark matter. Which one or both of them should be here, and what physical effect is that going to have on the number density of galaxies? So here's a cartoon picture of the simplest model of halo formation that's going to let me get to this quantity, the halo bias. And that is the following, where I imagine that I have some fluctuations in the matter field, like this, and rare fluctuations that are very large, and these high peaks that are above some value here are the ones that are eventually going to form dark matter halos. But if I have these perturbations sitting on top of a long wavelength fluctuation, that is, if I have these small scale perturbations sitting in an overdense region, then it's much easier locally to reach this collapse threshold. Instead of this global value that tells me when this mass forms halos, I only have to reach this local value, which is lower. And so this gives a cartoon picture of how the number density of halos, that is these rare regions in the density field that can collapse under their self-gravity and make halos by late times, fluctuates from place to place and depends on this matter density here. So one way of thinking about halo bias is that I have some function which tells me what the number of halos is, and it depends on local stuff, like the local mass density. And the number density of halos, therefore, will fluctuate spatially according to how the mass density is fluctuating spatially. And this coefficient here, which tells me how the number density of halos changes in the presence of a density fluctuation, is called the halo bias. And another, I guess, depending on who you're talking to, a bias sounds like a bad thing, but this is a parameter that astronomers can measure with galaxy clustering. Okay, so now let's think about our universe, which has both cold dark matter and neutrino dark matter. And we know that the cold dark matter and the neutrino dark matter don't behave exactly the same way. So on very large scales, the dark matter fluctuations are coherent with the neutrino fluctuations. But then on smaller scales, at later times, the neutrino fluctuations decay away, and that changes how these cold dark matter perturbations grow. And here is a reminder of my cartoons illustrating that. Oops. Okay, so now if I have these small scale perturbations sitting on a region with both cold dark matter and neutrinos, the effect of this long wavelength perturbation is going to be different here than here, where the cold dark matter perturbation is growing more slowly, and it may not help you form halos as much. Or the way in which the halo abundance fluctuates is going to vary. So my claim is then that the halo bias, which tells me how fluctuations in the matter generate fluctuations in the number density of halos, can depend on scale. In particular, it will be different for these small scale perturbations below the neutrino free streaming scale than it will be for these large scale perturbations that are larger than the typical distance neutrinos can travel. Here, this is something that I'm thinking about in the context of massive neutrinos, but there's actually some precedent for thinking about how scale-dependent growth of density perturbations can generate a scale-dependent halo bias. And that's by these authors here, Lam Hui, Kyle Parfrey, and Robbie Sheff, who looked at modified gravity models, which cause the density perturbations the evolution of density perturbations to depend on their scale, and found that these modified gravity models should give rise to some scale-dependent halo bias as well. So I couldn't quite adapt their techniques because they were looking at scale-dependent growth at very late times associated with the accelerated expansion. But just to point out that there's some precedent for these ideas, and there's interesting work by those papers. So the punchline is I want to estimate this quantity, the halo bias here, and how it depends on scale, or how many extra halos one sees in overdense regions. And again, this is interesting because this is some k-dependent function that astronomers can measure. And my claim is going to be that the cosmic neutrino background changes this in a way that is an interesting signature of massive neutrinos. So here's an outline discussing a cartoon picture of how to think about this. to get an idea of what this effect is. So here is my cartoon showing the distribution of cold dark matter at some early time when I think I understand it, and the neutrino dark matter, which is coherent on very large scales. There are two steps to figuring out the halo bias. One is to identify the regions in this field that will eventually collapse and form halos. So I determine a collapse threshold for the small perturbations to turn into halos in the presence, that's calculated in the presence of neutrinos and cold dark matter. And that allows you to determine what the initial sort of proto-halo distribution is. That is, look at the field, the matter field, and identify which peaks in this field can eventually form halos. To turn this into the late-time halo distribution, you need to identify these regions and then understand how they evolve gravitationally. So for instance, if I have a fixed number of sort of regions of proto-halos here that are sitting in an overdense region, at late times, that overdense region will collapse a little bit, and so that fixed number of halos will have a higher number density at later times because that region has collapsed a little bit. And conversely, in an underdense region, the number density becomes lower because that region expands a little bit. So, so my claim is that neutrinos alter both this process and this process. And in both of these processes, they introduce, that massive neutrinos cause a scale-dependent change to this process and a scale-dependent change to this process. Let's skip that. So carrying this out, what one finds is that the halo bias on very large scales, smaller than the free streaming scale, and very small scales, which are, sorry, I said the wrong thing. For wave numbers which are large, which are small compared to the neutrino free streaming scale, having a very large physical extent, the halo bias is different from the halo bias on for high K or perturbations which are small compared to the neutrino free streaming scale. And here's what this looks like. So this is what's shown on this axis is the halo bias, which is determined from, say, comparing the halo power spectrum to the total matter power spectrum as a function of wave number. So in a universe with only cold dark matter, this quantity should be a constant out to from very large scales down to small scales where nonlinear effects start to be important. But as I change the cosmology, in particular, adding more mass in massive neutrinos so that I have these scale-dependent growth effects and different clustering between different types of matter, the halo bias acquires this step-like feature where I have a constant value on very large scales and a different constant value on small scales. And the scale that separates these two regimes is this sort of neutrino free streaming scale. So the size of this feature is tiny. It's of the order of a few percent, larger for cosmologies with more mass and massive neutrinos, and smaller for cosmologies sort of at the normal or just normal hierarchy. But there is nevertheless a feature here. The amplitude scales with the energy density in neutrinos. In general, what I find is that there's a step feature, and the size of it has one piece which depends on the energy density in neutrinos here, and another piece which depends both on the energy density in neutrinos and the particular bias of the objects that you're looking at. So this is roughly the size of the effect. Now, I'll remind you that the fraction of energy in massive neutrinos is tiny. It has to be bigger than about 0.5%, but that's a very, very small number. So why would I care about such a tiny effect in the halo bias? And there are two reasons. One is because if you could measure this, then the halo bias, this feature in the halo bias can be used to constrain neutrino mass. And it turns out that you can measure that halo bias is a quantity that's not subject to cosmic variance. So this, in principle, could give you a measurement of neutrino mass that's not subject to cosmic variance. So that's in principle. And the other reason is that this change in the halo bias is small, but it's not small in comparison to the size of the effects of massive neutrinos that you would use to actually detect constrained neutrino mass. So this is potentially a serious systematic for measurements of neutrino mass from galaxy clustering. And here's an illustration of that. This is that same plot again with different colors showing the suppression and the matter power spectrum for different neutrino mass hierarchies. So normal, inverted, 0.3 eV mass in neutrinos, or 0.6 eV total mass. Now, this is the suppression of the matter power spectrum. If the halo bias were constant, then this would also just be the suppression of the galaxy power spectrum, because there's just some constant number b that I multiply both of these guys by. But now, I'm saying that the halo bias is not constant. It depends on scale, and in particular, it increases on small scales. So this plot shows the suppression in the halo power spectrum, including a calculation of my calculation of these scale-dependent bias effects. And what you can see is that the total suppression of the matter power spectrum is less than you would have otherwise thought if you had assumed a constant halo bias. So this degrades your constraints on neutrino mass, and it degrades them in a way that depends on the type of objects that you're looking at. So that could be a problem, because now your information is, you're less sensitive to neutrinos, and in a way that depends on the mass of the objects themselves. Now, the upshot. Here's these slices of the simulation again, showing the mass distribution and the galaxy distribution. If I wanted to measure it turns out that the fundamental limit on the bias, i.e. like the sort of Kramer-Rao bound on how well you can measure the bias of galaxies, is limited just by the number density of galaxies and the power spectrum. So as I get a really, really huge, dense sample of galaxy populations, the error on this quantity approaches zero. And this is in contrast to a measurement of the power spectrum, which is always limited to, fundamentally limited by the number of modes and the sort of amplitude. It's a statistical quantity that depends on the amplitude of the power spectrum itself. And this is similarly true for the ratio of the halo bias factors. So here I have that same slice showing a galaxy population, showing the distribution of galaxies from that simulation. And then this image over here is supposed to be a cartoon showing a different galaxy population. I've actually just turned up the contrast on this image, but this mimics what it would be like to look at a distribution of, say, more massive, rarer galaxies or brighter galaxies, which trace the matter in a slightly different way. So with multiple galaxy populations, you can in fact measure the ratio of the biases in a way without cosmic variance. So for instance, if you had a spectroscopic survey with a huge number of galaxies, you could measure the ratio of the galaxy bias parameters, and these curves show calculations of the scale-dependent ratio of the biases due to this massive neutrino effect. So with a ridiculous number of sources, here I have hundreds of millions of, a few hundred million spectroscopic sources, one would actually be able to resolve the scale-dependent feature and get a cosmic variance-less limit on the mass. Unfortunately, this is a huge number of sources, which is not even with things like DESI or sort of any near-term spectroscopic surveys that I'm aware of. Would you be able to get error bars small enough to resolve this?
That's just too narrow.
You know, I haven't checked. I think that HEPEC's, maybe. I don't think HEPEC, so it turns out that just not many surveys are in this limit where this number is very, very small. But yeah, I'm still in the process of going through and making more precise forecasts for various surveys. So I don't have a final answer to that. Fortunately, with a photometric survey where you have not as precise redshift information, but can measure instead sort of angular power spectra. This scale-dependent feature in the bias seems to persist. So with an LSST-like number density of sources, I think that even though this scale-dependent feature is smaller in the angular power spectrum, I think one might actually be able to see it. So that's cool, and there are, of course, all sorts of potential astrophysical and observational systematics that would have to be taken into account. So I'm sort of in the process of pushing this ideal situation as far as I can to see whether it's something that could be seen with realistic surveys, even in the ideal case. But developing, understanding things more, understanding what types of astrophysical systematics and so on could mimic this is another challenge on its own. So I think I'm going to skip these next discussions, which are about how the abundance of halos has changed and how neutrino halos accrete around cold dark matter halos and how they're puffier, and that's very interesting. There is probably a huge amount of neutrino mass around galaxy cluster-sized halos, like things like 10 to the 10 solar masses of neutrinos, but I don't, it would be very challenging to detect it because it's a tiny 10 to the minus 5 or so of the total mass of the galaxy cluster is probably in massive neutrinos. But that's nevertheless fun to think about for future surveys. So in summary, I think this picture of our universe with multiple types of dark matter is very interesting, and there are potentially new effects to be thinking about and old effects that we might need to think more carefully about as the data gets increasingly precise. But it's an exciting time to be thinking about neutrinos, and cosmology absolutely will have something to say, or will potentially have interesting information about the masses and the total number density of neutrinos in the not too distant future. The thing I focused on today was the scale-dependent halo bias, which is potentially a new signal of massive neutrinos, but also is systematic if not taken into account. But there are other interesting things to be thinking about as well. Thanks.
Thanks. Is there any more questions for Marilena?
Yeah.
Yes.
Your study does change if you have a type of dark matter from the fermion or the boson. Does matter or doesn't matter?
The regular, like the cold dark matter? I don't think that affects anything here.
The second question is scenario change from non-thermal to thermal scenario.
Of the cold dark matter?
Yeah.
I don't think any of the thermal, we know that as long as it's cold enough to be acting like the cold dark matter that we think that we have, that forms the backbone of structure, these are all pretty large scale effects that aren't sensitive to making it a little bit warm or making it axions or something like that that's non-thermal. As long as it's, given the current constraints on how cold dark matter is, I think it's okay. For neutrinos, it's interesting to think about, I think these questions of like how much neutrino mass ends up getting bound around halos is interesting if you had sterile neutrinos that weren't thermally populated or something. You might be able to do, you might be able to get, so here's this expression for how much neutrino mass accumulates around dark matter halos, and I've written it all in terms of the mass, but that's actually not precisely true. It depends very strongly on the temperature and the distribution, so you might, in that sense, on the sort of neutrino side, things could be interesting. Would be very different if you change the distribution. If you made it non-thermal. Yeah.
Is the dynamics of the correlation between dark matter and neutrino halos fast enough that you don't have to care about how slowly things are moving? Fast.
How slow which things are moving? Or?
Well, it's not necessarily static, right? I mean, your problem practically the way you describe this looks like static, because if whatever the processes that put the neutrino halos in correlation with dark matter halos, they're fast.
Yeah.
Right? So are they?
Yeah. I'm not sure if you're asking, this is the question you're asking, but there is something super interesting that we realized, which
in
is...
the sense, if you go to surveys of larger redshifts, you begins to matter, whether it's too early, too late, what you see.
Whether what's too early or too late.
Trying to parse the question, so I think you're asking is there like any dynamics?
Right.
Well, I think that's, so you make these clustering measurements at some sort of redshift, right? And that's basically it. That's your picture of structure formation at that redshift, right? And whatever dynamical processes that happen before then. That's captured at some level by her calculations, accretion type calculations.
Well, just the calculations didn't really have any time parameter in a sense. It looks like it's all already correlated, it's all settled. This is,
I guess I'm a bit confused. So for sure, these, all of these types of, this type of thing, this suppression and the power spectrum is, this is absolutely related to Rhodopsin's dynamics, but this is time evolution generates this difference between the different scales.
So if you plotted that in a different time, right, you'd see different levels of suppression.
That's right.
So it is dynamic in that sense. This statistic, this is statistical.
I guess this happens in lots of cosmology where we're doing statistical calculations, but the things about evolution sort of come into the shape of the statistics, sort of the scale dependence of the statistics reflects something about the dynamics. Like, I guess the Baryons oscillations are the classic one, so that's coming from, we're measuring one statistic, but it's reflecting something about something about the evolution. But I'm not sure if I'm understanding your question correctly.
I'm not sure I understand my own question. So it's...
Okay, so is there any other questions? So this delta, this bias between different types of galaxies, I think is what you called it. Is how evil is that? In terms of the systematic.
I'm not. You mean?
I think you were talking about, so B1, B2 is that by some different population of galaxies.
Yeah,
You're
exactly.
looking at like
exactly.
luminous red galaxies and similar.
Yeah, so I'm imagining
Okay.
that I don't have. If I have a lensing measurement, then I get the mass. But if I don't have lensing, I can only measure the ratio of biases. Yeah, so I think it. I think it's potentially important in the sense that this change here that I'm drawing is dependent on the population that you're looking at. Now, where the information about neutrinos comes from in surveys is not just from this shape. It comes a bit from redshift space distortions, if you have spectra, or from there are other places where neutrino mass comes in besides here. But so at the end of the day, I'm not sure. It probably depends a lot on the survey and whether you model this effect or not.
And bias kind of makes it sound like a bad thing. Right?
Yeah.
It's their preferentially clustering.
Yeah, we need
It's
to
not
astronomers
like
need to know word for this, I think, right?
Yeah, that's why
Yeah.
that's why I have this like the parameter that some function that astronomers can measure, but.
It's evil slides. Okay. Anyway, so is there any more questions? So okay, let's cycle again.